Well, hi there, and welcome back to the wild world of volcanoes. This is part two. You should have already seen part one. Well, in part two, we're going to talk about igneous rocks, uh, magma and lava, the difference between plutonic and volcanic rocks, the formation of magma, the attributes of magma, including viscosity, which is a critical property, as you will see, and the very nasty volcanic gases that come out of these volcanic eruptions. Okay, igneous rocks are those that cool, solidify, or crystallize from a molten magma or lava. We classify them according to their texture and their chemical composition. Based on texture, we classify them as either volcanic or plutonic. A volcanic rock is one that cools from lava on the surface. They cool very quickly, so the crystals don't have time to grow very big. So we have a fine-grained aphanitic texture. Plutonic rock cools from magma below the surface, so they cool at a slower rate, and the crystals have time to grow bigger, to a bigger size. So the texture is typically coarse grained that we call phaneritic. Now, some rocks will have a dual uh, cooling history. Think, for example, of a magma that begins to cool below the surface. Some crystals begin to develop. Those are fairly large size. But then this magma is extruded on the surface as lava. So the rest of the melt cools very quickly from the lava. So what do you get? You get a rock that has large crystals surrounded by a bunch of small crystals. The large crystals are called phenocrysts. The fine-grained crystals are the matrix. Here's a picture of the Devil's Tower in Wyoming. It is made out of phonolite, and the phonolite is typically porphyritic. You can see the white phenocryst surrounded by the darker matrix. Based on their chemical composition, we classify igneous rocks as either felsic, intermediate mafic, and ultramafic. Felsic rocks are rich in the mineral quartz. Mafic rocks typically do not have any quartz. They're rich in the ferromagnesian minerals. Those have a lot of iron and magnesium, and also some of the calcium-rich plagioclase feldspars. Intermediate rocks fall somewhere in between the felsic and the mafic. And then you have the ultramafic rocks, which is mainly what the Earth mantle is composed of. Those are the supermafic rocks. Let's briefly talk about the rock cycle because all rocks are really related. Now, this is a cycle, so you can start anywhere. But since we're talking about volcanoes, let's start with magma at the bottom of the diagram. Uh, Igneous rocks form from the cooling, the crystallization, or the solidification from magma or lava. When these rocks are exposed at the surface, they are now exposed to the agents of weathering and erosion. That can be water, that can be ice, that can be wind, etc. The bottom line is that these rocks are going to be broken down by physical processes, chemical processes, or combinations of both. Uh, Sediment is then created, sediment being this broken down material. The sediment can be now eroded, which means it is transported and at some point is going to be laid down somewhere, undergo what we call deposition. The sediment then is now going to be buried and compacted and cemented. That's the process that we call lithification, or the transformation of sediment into sedimentary rock. Sedimentary rock can be buried, and because of the action of heat, pressure, and chemical solutions, can undergo metamorphism and transform into a metamorphic rock. So you can create a metamorphic rock through the action of heat, pressure, and chemical solutions without going through the molten state. Metamorphic rocks can be further heated and then melted, and you're back to a magma. Now, there are some shortcuts to the cycle. For example, igneous rocks may melt, and you're back to a new magma. Or igneous rocks can be metamorphosed. Also, sedimentary rocks and metamorphic rocks can weather directly, giving you new sediment. Those are the shortcuts in the cycle. So magma and lava are masses of molten rock composed mainly of silicate minerals and dissolved gases. Magma is the term that we use when this molten mass is below the surface. Lava is the term that we use when this molten mass is located on the surface. Uh, Magma and lava are associated with plate tectonic boundaries or hotspots in the Earth mantle. By the way, the picture that you see here is a lava flow associated with the El Teide volcano. It's located on the Isla de Tenerife, Islas Canarias, España. Now that's Castilian Spanish, huh? That's my native language. It's pretty cool, huh? Now here's my sketch showing you the three types of plate boundaries: the divergent boundary, the convergent boundary, and the transform boundary. The divergent boundary is, in essence, where new crust is created. Magma rises from the mantle, from the asthenosphere. It splits apart the lithosphere, and you are creating new crust. That's typically your mid-ocean ridge. Then you have your convergent boundary where two plates come together and one is typically thrusted below the other one. That's what we call the subduction zone. And then you have your transform boundary or your transform fault where one plate simply moves past the other plate. I should point out to you that magma is associated with both divergent and convergent boundaries. Now, volcanic rocks form from the cooling of lava on the surface. So, as I said before, they have typically a fine-grained aphanitic texture because they cool very quickly. The crystals don't have time to grow. The plutonic rock cools from magma below the surface. They cool much more slowly, so the crystals have time to grow to bigger sizes. They develop a texture that we call phaneretic. By the way, plutonic bodies tend to be associated with almost every major mountain range throughout the globe, the world. In the picture here, I'm standing at an outcrop of some pretty impressive basaltic lava flow. It is the Bonito basaltic lava flow that you find in the Sunset Crater area near Flagstaff in Arizona. Now you should know that magma forms either at the base of the crust or within the uppermost upper mantle. Once magma forms, it has to rise uh, because of its low density. Its density is lower than the solid rock. How does magma rise? Well, any way he wants to. Who's going to argue with magma, right? Well, actually, there are three processes. One would be the process of assimilation, where the magma melts or dissolves the rock around it and above it. Uh, the other one is what we call magmatic stoping. The magma actually exerts pressure on the surrounding rocks and the rock above it, so it breaks it into blocks, which are more easily assimilated. Or magma can always find a pre-existing plane of weakness, like a fracture plane or a fault plane, and shoot through it. I'm standing here on a basaltic lava flow, an lava flow near Kilauea volcano in Hawaii. Now, magma is composed mainly of silicate minerals and dissolved gases. The magma has all sorts of chemical elements in it, but to us, the most important ones are going to be oxygen, silicon, aluminum, potassium, sodium, calcium, iron, and magnesium. The viscosity of the magma, the thickness of the magma is very critical to us because it controls the violence of the eruption, the explosivity characteristics of the eruption. Viscosity is controlled by three things: silica content, temperature, and the amount of dissolved gases. We can say that viscosity is directly proportional to silica content and inversely proportional to temperature and the amount of dissolved gases. And you say, what? What did you say? It's not that difficult. Viscosity is directly proportional to silica content. So that means that the higher the silica content, the higher the viscosity. Conversely, it is inversely proportional to temperature. The higher the temperature, the lower the viscosity. It is also inversely proportional to the amount of dissolved gases. The higher the amount of dissolved gases, the lower the viscosity. The main volcanic gases that we find are water vapor, H2O, and carbon dioxide, CO2. Between these two, you have 90% of the volcanic gases. But there are other gases that come out of volcanoes that are pretty nasty. You have sulfur dioxide, SO2, that's pretty bad smelling gas, and you have then some of your acids and your lethal gases. You have hydrogen chloride, HCl, that's basically hydrochloric acid. You have hydrogen sulfide, H2S, it is a lethal gas. You can have carbon monoxide, it can kill you too. Hydrogen fluoride, it's pretty bad. So there's some pretty nasty gases that come out of volcanoes. At this time, I want to remind you of the infamous nuée ardente, this incandescent cloud of gas and ash, this fire cloud that scorches and suffocates. These lethal clouds have temperatures on the order of 1300 degrees Fahrenheit. They can move at 200 miles an hour. Well, guess what? We have finished part two. So see you in part three.